Draw a picture for you. Let's see. Okay, I have this. I have this. 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 I have this. And this goes like this. This goes like, could have drawn this maybe better. That. And those nodes 1, 2, 3. So your question is, what kind of circuit is this, and what's the common name for those nodes 1, 2, and 3?
All right, it's looking like it would be you would have node 1 would be input, node 2 would be Q, and node 3 would be the clock. And it looks like it would be a sort of latch, however, it doesn't exactly match some of the stuff we've done in the class.
So you think it's a latch?
Possible. It doesn't loop back with the current configuration, but with a few more elements, it could.
It doesn't look by. What is this terminal 1? You said this is input. Is that the normal name for it? If this was a latch, you said you have a clock and a Q, and you call it input in a latch, or do we have a different term? What's the input to a latch called, where the signal comes in?
Where the signal comes in, D input.
Yeah, D. Yeah, you have this 90% right. This is a latch. It's a special kind of latch. It's a D latch, right? Because we have a D input. And there's something else special about it. You said there's no feedback path. So what happens if we don't have a feedback path?
Then it's only transparent when the clock is, in this case, high.
Clock is high, it's transparent. It'll feed through. When clock is low, it'll remember. And how does it remember?
It remembers. I'm thinking volatile, but I know that's not the correct word for it. It's dynamic. That's
Yeah, you got it. It's a dynamic D latch because it remembers, like, if something is charged is stored on this capacitor, which is just the input capacitance of this inverter, but it leaks, so it's dynamic. You have to clock it at some minimum rate, otherwise it'll lose its brain. Won't remember. Yeah, so you got it.
All right.
Good job.
Thank you.
I teased that out of you, the whole answer. Okay, next is Max. Max. So you here, Max?
Yep.
Great. Okay. Oh, we have to draw a picture for Max. I'm gonna draw. So you can assume that's a transmission gate. There's a P signal on the other side. I just haven't drawn it here. Oh, sorry. There's a bubble here. So these are the opposite control transmission gates. This is node 1. This is node 2. And this is node, sorry. And this is node 3. So why don't you tell me what kind of circuit this is and label the nodes 1, 2, and 3.
Okay, so this should be a D latch with just CMOS, so
Yeah.
with just transmission gates. So number 1 is D. Number 2, this should be Q naught, and by extension 3 should be Q. I don't know. I think it's missing a capacitor, but I'm not. I think it would work without the capacitor, but it's like it might be missing one right before the first inverter in the top.
Yeah, you're right. So it's a D latch. We call this a static D latch. And there is a capacitor here, but we don't need a capacitor. There's always parasitic capacitance at every node in a chip, but we don't need that, because what happens is, like, let's say you go through here and you put a 1, and you have a 1 here and a 0 here, right? And this is, so then when you switch this one off and you switch this one on, this is a feedback path. It doesn't really rely on this capacitor. Like, there can be leakage current through the diode here. It doesn't matter. This inverter is providing lots of current to force it to stay at 1. So it doesn't need that capacitor. That's why it's static. Yeah, you got it right. Does that make sense?
Yep. Yeah, that makes sense. It's just like in 2607, I think the one thing that I remember from that course is are the two inverters that are hooked into each other. And like that being stated as the fact that like that won't work or something. Because of the fact that there's like only 180-degree phase inversion or something like that, but I don't exactly remember.
This will work. Like, it'll remember what state it's in. Like, if this is a 1 and a 0, it'll just keep recirculating once the switch is closed. Or if it's a 0 1, it'll just keep recirculating. Yeah, oh, it'll definitely work.
Okay. Yep.
Yeah. Gee, the one thing you remembered was wrong. It must have been some special case or something. I don't know. I wasn't there. But anyway, you got a bonus point. Let's see. Do we have another question? Yeah, we have one more question here. Let's see, who's this for? Maven. You hear Maven? Oh, Maven. Okay. Oh, we're down at the bottom. How about Jason? You hear Jason? No, Jason. Let's go back to the top. Mina. Oh, Mina. Isaac. Oh, only have one question left. Mingzi. No, Mingzi. Everybody, nobody's here. Peter.
Yeah.
Oh, who's this? Peter?
Yeah.
Okay, Peter. One more question here. Okay, Peter, I'm gonna draw a picture for you. Okay, Peter, here's the circuit. I want you to explain to me, how does this circuit work? And are there any advantages to this circuit? I guess first off, do you know what this circuit is?
I think it's a flip-flop.
It's a flip-flop? No, that's not true. It's not a flip-flop. Actually, I'm gonna erase this. Not a flip-flop.
A latch.
Hello?
Can you hear me?
Yep,
A latch.
it's a latch, yeah. It's a static D latch. So how does it work?
So when the clock is low, the D input goes through.
When clock is low, so C is our clock, but you're saying when that's 0, so this will equal 1. The D input's gonna go through?
Yeah.
Really? This is 0 going into NMOS transistor. This is 1 going into a PMOS.
Also, when this, wait, no.
What's this thing right here? Do you know what this is?
That's I need the
We have a name for that.
VDD.
Oh, sorry, yeah, that's VDD. This whole thing, these 4 transistors together, what do they make? Oh,
Is it a switch?
no.
No. Oh, yeah. I don't know.
Okay, we're gonna move on. Orit or Orit. No. Oh, Michael. Can you hear Michael Jones?
I am here, but my answers have already been said. I'm not entirely sure. Any new
Okay.
answers?
We're gonna pass. Brian, are you here?
Yeah, I'm here.
Okay,
So
Brian.
what this is a clock converter latch. So you
Yes,
want me to
you're right.
explain
It's
it?
a clock converter latch. Yep. So how's this work? Like
So-
when clock is low, what's going on?
Yeah, so when the clock is low, we know that we have an input signal. Like let's say we have an input signal of 1. We can see that since both clock is low and it's in series with the D input, we know that it comes from the bottom of ground and it circulates up to the first inverter, which then inverts to a 1. And
When clock is
effectively,
low?
when our clock is low and our D input is low.
Clock is low, yeah, and D is
Yeah.
low. What's
Yep.
what's gonna happen here? Say
So
rating.
that's what I'm saying. There's going to be a 0 there, right? Because both clock is low and our D input's low, and those are both attached to NMOS, right? So that ground below that is going to be attached to that effective Z.
When you take an NMOS and you put a 0 into it, what does it do to the NMOS?
Oh, true. Yeah, that's not on. Yeah, no, that's facts. Yeah, that's not on. Okay, so when your clock is high, sorry
Okay,
about that. When your clock is high, you have
hold a sec here. I'm gonna erase this. You want this high?
just confusing because you put C bar equals 1. So that's just an inverted clock. Okay.
Yeah. So this is 1. So C bar will equal 0.
Mhm.
Over this here's 1, 0. Yep.
Yeah. So effectively, you push through a 1 from VDD. You push through a 1 through this inverter. And at this point,
what's going on right now? What you
Okay,
want
so
D to
you-
be 0 or 1 or
yeah, you want your D to be 0 because when your
Yep.
D is 0,
Yep.
your PMOSs are on.
and so
Yeah.
your C bar equals 0. So your PMOSs are on. You latch through a 1 from VDD. That 1 is then inverted to the Q output, and then it cannot be passed through anymore, as you see our clock is inverted as opposed to the other side.
Yeah, so this one's not driving.
So that's not driving anything.
Okay,
But
so this
when the
D went
clock's-
through, it was
Yep,
transparent.
this D went through transparent.
Yep.
And then when the clock switches, this D will be latched in and will no longer receive a new D input until the next low clock.
Yeah, this will turn on, this will be 0, and this will
Yeah.
feed back.
And it'll latch
sorry,
through and
this
it'll be
will be
inverted
1.
to the output again.
Yep, this will feed back.
Yep.
Yeah, so it's a static D latch using tri-state buffers, or whatever you want to call them.
Yeah,
So is
clock
there any
inverter
advantage
latch.
to it? And it's transparent high.
Yeah.
Yeah. So is there any advantage to this?
So I remember the advantage to this was you didn't really need. So sorry, with this, so it reduces the actual interaction with like the source resistance. That was one.
Yeah. The alternative way to do this is like
The transmission gate, yeah.
Yeah, like this, and then an inverter.
But then you
And
get
this has some
RCFX.
resistance. Yeah.
Yeah, you get RCFX. So with this, you avoid the RCFX, and you still have your inverter or control inverter states.
Yeah. Yeah, that's good. See, the other advantage is that if, hey, say this P channel was broken, it still kind of works. But here, if this P channel breaks,
Completely broken, and
you'll
you can't
know it.
use
It'll never be able to pull high, so it breaks it. It fully breaks
Yeah.
it when one of the transistor breaks. This one only partially breaks, and that's a bad situation if you're only kind of partially broken. It's kind
So
of
it's effectively
functioning, but
easy
not
for
so great.
testing.
Okay.
And you have also 10 transistors as opposed to 12 or 16.
Yeah, it has more transistors, so that's a disadvantage.
Yeah.
You have to have another inverter here for
Oh.
C and C bar. That's a disadvantage, but it's not a big disadvantage because turns out the layout of this is very efficient, so they're similar size. Yeah. Okay. Wow, you got 3 points there, Brian. Okay, that's the end of bonus questions. We are going to move on to the next